Okay, let us resume our lecture from the question number 2. In the question number 2, how much work is done when you push a crate 100 Newton across a 10-meter factory floor? So it is very simple question. We need to find out the work done. We know the relation for the work done. F dot T as the applied force and cover distance are in the same direction. So the angle between them will be equal to 0. Then our relation will become FD cos of 0 degree, which will result FT. What we need to do, we need to put the value of the force, that is 100 Newton, and value of the cover distance, that is 10. It will result you work done 1000 of joule.
Why
That
was
is
there
work done.
FD cosine?
Because it is a formula dot product in the vector. You know there are two types
Oh,
of the multiplication,
yes.
vector dot product. Okay, so in the second part, if the force of friction on the crate is 70 Newton, show that kinetic energy gained by 300 joule. If the force of friction is 70 Newton, while the total force is 100 Newton, then what will be the net force? Because you know, force of friction is always against in direction to the applied force. So you need to subtract 100 minus 70, that will result 300 Newton. So 300 Newton is the net force here, and show that the kinetic energy gained by crate is 300. So as we know, the work energy theorem is equal to change in kinetic.
How was 100 minus 70?
Okay, again listen to me.
300.
Here you can see the applied force is 100 Newton in the first case, and in the second case he is saying that force of friction is 70 Newton. And you know, force of friction is always opposes the direction of motion, and it is always opposite in the direction of applied force. So we are here calculating the net force 100 minus 70. 100 is applied force, 70 is a force of friction, and remaining is 100 minus 70 is remaining is 30 Newton force.
Oh, 30, not 300.
Yes, 30 Newton
Okay.
force. And for
Sorry.
the 30 Newton force, show that the kinetic energy gained by the crate is 300 joule. So here we need to show the kinetic energy gained is equal to 300 joule. For that purpose, again, we need to calculate the net work done here is equal to FD. F is the net force, that is 30, and D is the cover distance, that is 10. So 30 multiplied by 10 is equal to 300 of joule, that is kinetic energy. So he was saying that we need to prove 300 joules. So we have what becomes of the missing energy? That is the third question. Initial energy is 1000 joule, and net force energy is 300 joule. The remaining energy or the missing energy that is dissipated as a result of friction is equal to what you need to do. Here we have two type of the energy. One is the work done due to the applied force. Other is the work dissipation or the work dissipation due to the force of friction, that is 70 Newton. And 1000 minus 100. If you will subtract 1000 minus 300, then you will receive 700 of joule, that is missing energy. Where it is going, it is actually the dissipated energy as a result of friction. And you can also calculate it in another way from the work done. FD is equal to, as applied force of friction is in the direction opposite to the cover distance. So here the angle that you will use is cos of 180. Which will results minus FT. It is not part of our question. I am just making sure you are understanding. So as the force of friction is 70 multiplied by cover distance is 10, then your dissipation of the energy is 700 joule. How can we say it is dissipated energy? Because that is a negative sign, that is showing that it is actually the missing energy or the dissipated energy. Is it clear?
Yeah, it's clear.
Okay, have a look here. Okay, data for the given pushing force 100 Newton, cover distance 10 Newton, force of friction 70 Newton. That is given to us. In the first case, you need to find the work done, and in the you need to check it here. In the statement, they are not giving us in the first case the force of friction. So here you can see in the first part they are not giving us the force of friction. So we are ignoring the force of friction in the first case. We are just calculating the work done. Fd is equal to Ft cos of theta is equal to cos of 100 multiplied by the 10 is equal to 1000 joule. But as we can see in the second case, he is saying that if the force of friction is 70 Newton, show that the kinetic energy gained by the crate is 300 joule. So for that purpose, show that kinetic energy is equal to 300 joule. So F push minus F force of friction, then the net force is 30 Newton only. So work done by the 30 Newton is equal to 300 joule. So the net work is 300 joule. Where is missing energy? Total work done minus work done by the net force is equal to the missing energy. That is missing energy. Is it clear?
Yes, it's clear.
Okay, so let me clear the area. Okay, let us discuss the question number 3 now. A carton air track is moving 0.5 meter per second when the air is suddenly turned off. A cart is moving at 0.5 meter per second when the air is suddenly turned off. The cart comes to rest. What does it mean? Its final velocity is equal to 0, while its initial velocity is 0.5 meter per second. Traveling 1 meter. It is traveling 1 meter and getting rest. Final velocity is 0, initial velocity is 0.5 meter per second and covering 1 meter distance. Okay. The experiment is repeated, but now the cart is moving 1 meter per second. Initially, it was moving 0.5 meter per second. Now, after repeating the experiment, now it is moving with 1 meter per second. The air is turned off. It means its final velocity again will be equal to 0 because it is coming to rest. How far does the cart travel? That is our question. That how far does the cart traveled? We have to measure its cover distance in the second case when its velocity was 1 meter per second. So what is it here? They are giving to us initial velocity v1 0.5 meter per second and final velocity vf equal to 0. Second case, and here in the first case the cover distance d1 you can say is equal to 1 meter. Now for the second case, initial velocity, as it is second case, I am writing v2 is equal to 1 meter per second and turned off, so final velocity is again equal to 0. And what you need to calculate here? d2 you need to calculate here. Cover distance in this case we have to calculate. Okay, for the both cases we need to use the work energy theorem again because it is moving and work is done on it. Its velocity is getting changed. So as a result of applied force, some work is done on it and it is covering the distance. So according to the work, but we don't know about the applied force that we have to calculate. It can be the force of friction of the air that we have to calculate because it is moving because of the force applied by the air. So net work done that we know is equal to change in kinetic energy is equal to, okay, if it is equal to change in kinetic energy, and I'm finding space to write. Okay, so FD we can write FD1 is equal to half m, as its final velocity is equal to 0. We can write directly final velocity is equal to 0. Okay. Initial, final, yes. Okay. Initially, its initial velocity has some value, you can see, because initially it was moving with 0.5. It is not a final, it is initial velocity. So, initial velocity equal to 0, having value some 0.5 square, and we need to simplify it. As we are here to calculate the force, so we need to change our relation 1 by 2, as the mass is not given to us, m multiplied by 0.5 square, that is velocity, divided by d1. d1, d1 is 1 meter, so I'm just putting here 1 meter, and it is giving us the value of the force F. So after simplifying it, I have the relation is equal to F1 0.5. I can write 1 by 2 as a 0.5. Here it is also multiplied by 5 square, 0.25 it will become 25 m. And in the denominator you can write this 2 as a 2 like this. This is the applied or the force enduring that case. You can consider it. Okay, now we have the force. What we have to find? We have to find the D2. Again, we need to apply the work energy theorem on the second case. F D2 is equal to half mv square. So isolate the D2 because you need to measure the D2 is equal to half mv square divided by F. Put the corresponding values 1 by 2 multiplied by some value was here given to us, that is for the force. Where is force? Yes, on the other side. 1 by 2 multiplied by m multiplied by v square. V, as here it was v1 divided by force, that is equal to, from our this relation, 0.25 m over 2. 0.25 m over 2. What you need to do? You need to cancel this m by this m and simplify the other relation. That will result you some value. Yes, you can also cancel this 2 by this 2, and 1 by 0.25 is the remaining value here. That will result you 4. So the second covered distance when the velocity was 1 meter per second is d2 equal to 4 meter. So what was the question? In this question, we were thinking that a velocity of the air that is applied on the object is moving with the 0.5 meter per second, and suddenly air stopped. As a result, it come to rest and cover a distance of 1 meter. In the second part, again repeating the experiment, it was moving with the velocity now 1 meter per second and suddenly it turned off its air and now it is stopped, coming to rest. What you need to find? You need to find it how much distance it has covered in the second time. So let us check. V naught For the initial case, 0.5, d cover distance, and now stopped, its final velocity is equal to 0. Similarly, second case, initial velocity 1.0 and d is equal to that we have to calculate. D prime, I'm here saying d prime. Okay, fractional force is equal to constant in the both cases because same air is applied here. So change in kinetic energy is equal to net work done is equal to V naught square minus 0 square FD, simplifying. Isolating the F, force of friction is equal to 1 by 2 mv naught square over d, simplifying. And now I have the relation for the force of friction, and force of friction is same in the both cases. So in the second case, change in kinetic energy is equal to W net is equal to 1 by 2 m into 1 square minus 0 square F of d dot d prime, simplifying d prime, isolating 1 by 0.25 is equal to 4 meter is the distance that is covered when the object was moving with initial velocity 1 meter per second. Is it clear?
Yes, it's clear.
Okay. Okay, now we are on the question number 4. It is also an interesting question. This is typical driver lessons question. A car move 50 km per hour, skids 15 meter with locked brakes. Same car, same road, and that car is moving with 50 km per hour speed and skids 15 meter on with locked brakes. How far will car skids with the locked brakes if the speed is 150 km per hour? Now the speed is increased to 150 km per hour. Now speed is a bigger value. So it is understood that its skidding distance will also be bigger, but let us check how much it will be. Okay, here V1 is equal to 50 kilometer per hour, and we need to change it into meter per hour. Yes. Okay, we will check it at the end that we need to convert it or not. V2 is equal to 150 kilometer per hour, where first distance S1 you can say is equal to 15 meter. And S2 is the distance, skidding distance during second velocity that we have to calculate. Okay, as it is skidding and finally it will stop, and we can say that its final velocity can be equal to 0 because if brakes are applied, finally it need to stop. So we are applying the third equation of motion, that is Vf square is equal to Vi square plus 2as is the acceleration of moving vehicle, s is the cover distance. As we are applying it on the first case, so 0 is equal to V1 square. V1 is initial velocity in the first case, 2as. As it is skidding, then I just want to separate the acceleration. Then our relation will become V1 square divided by 2s, but with a negative sign. It is as it is skidding, brakes are applied. Now instead of the acceleration, we will say it is actually deceleration. So if it is deceleration, and we need to also understand, as in the both cases, same vehicle is used, same roads are used, same brakes are applied, so deceleration will be same on the both cases. So instead of using deceleration in vector form, we need to use its magnitude, 2s, 1. As we're talking about the first case, so to S1, we need to isolate the S1 distance, then our relation will become, or you can just continue with it. Later, we will check what we have to do. Okay. Then you can say this is an axle of relation for the first case. Now we need to say similarly for the second case. A2, as the acceleration is same, so we need not to give any number to it, is equal to V2 square divided by 2S2. So let us compare these two equations. As a result of comparison, our relation will become V1 square by 2S1 is equal to V2 square by 2S2. Here you need to cancel the 2 by the 2 and isolate the ratios. S2 divided by S1 is equal to V2 divided by V1 square. Whenever you will understand, later you can observe the ratios, then you need to not to change the units from the kilometer to meter or kilometer per hour to meter per second, because in the ratio they will be cancelled out. 150 divided by 50 whole square. So 150 divided by 50 will result 3 square will result 9 is equal to S2 divided by S1, but you have to find the S2. So isolate the value of the S2, then S2 will become is equal to S1 multiplied by 9. Okay, we need to put here the values. S1 is 15 multiplied by 9, it will result 135. So as a result of second case, when velocity is 150, then the skidding distance will be 135 meter. Is it clear?
Yes, it's clear.
Okay, I think you're tired.
Yes, a little bit.
Okay. Okay, here you need to have a look here. Given velocity for the both cases, what you have to calculate second distance from the third equation of motion, putting the values, simplifying, isolating the acceleration, as the acceleration will be same in the both cases because same car, same road, same brakes are applied. So acceleration is equal to V1 square root to S1. Similarly, for the second car, A is equal to V2 square root to S2. You need to compare these values, cancelled, and isolate the S2 or S1. And S2 is equal to S1 multiplied by V2 or V1 square. Put the values, simplify, and finally you have the corresponding answer. Is it clear?
Yes, it's clear.
Okay. So for tomorrow, what will be the time of our lecture?
When would you like it to be?
Okay, then I think 7 p.m. is better.
Okay, let's do 7 p.m.
Yes. Okay, now we are on the question number 5. Yes, we are on the question number 5. It is also another interesting but a little bit lengthy question. Okay, you need not to read the whole thing, just you need to read from this point. The worst case operating parameters that are considered here for a car consists in maintaining a steady 120 km per hour speed during 500 km trip. Of course, this might not represent the actual worst case scenario, but it represents a good situation to fix some ideas. Okay, the main point in the start of our lecture, I think we have focused on it. To maintain a constant speed on the flat road, it is necessary force provided by the car engine must be equal to the drag force plus force of friction. That is the main thing we have to prove here. What we have given here, the mass is given, drag force constant is given, and area is given. And here I want to write this statement in terms of equation. So force provided by the engine is equal to force of friction plus next was drag force Ft. That is actual equation. And let me open this equation. First of all, I'm writing the drag force 1 by 2 rho A CD V square plus drag force, force of friction, we can write it mu n because n is a normal reaction. So we can make it more better equation just by putting the values 1 by 2 multiplied by rho is air friction 1 by 2 multiplied by area that is given 0.7 multiplied by CD is just drag force constant 0.28 multiplied by V square that is where is that? Let me find where is that value of the V square. Yes, 120 kilometer per hour is V square, but before that we need to convert it from 120 kilometer per hour to meter per second. Then it will results you 33.33 meter per second. So put it here 33.33 square plus second quantity mu n. Mu is a coefficient of friction and n is normal reaction which is equal to mg. Then our equation can be written as mu mg. And here you can put the value of the mu that is given here. Here, what is that? Yes, it is 0.015. 0.015 multiplied by mass was 1000 kg. 1000 multiplied by 9.8. Okay, let me show you what you have to find. What is the power required to overcome these dissipative forces? Which these dissipative forces? These two dissipative forces. One is the force of friction, other is the drag force. On these forces, how much power is required to overcome? So, after solving this whole equation, our results are for the drag force 133.36 Newton plus force of friction is 147.15 Newton, and here you can see force of friction is greater than the drag force and it is also necessary, and we need to round it off closer to some 10 value. For example, if it is 147 and it should be 147 and it should be 130.5 plus 147.5, it will result you some force that is 277.
Why do we round it like that?
Just closer. I want to close it to closer value. If you don't want to round it off, you can, because one thing that you need to do, you will need to also round it off. It will become 150. And in that case, it will give you the 280, but it is actually not the actual value. It is estimated value. So the value of the force is now found. You can say it is a Newton. But what you have to do, you have to find the power required to overcome these two dissipation. For the power, you have the formula. Power is actually the product of force and velocity. Force is given, but velocity is also given. Product of force and velocity. Velocity, yes. You need to put the values 280.5 multiplied by velocity 33.33. It will result some value that will be, I think, 9.249, but after rounding off, it will become 9.25 kilowatt. Yes, that is the power that we have to find, and this power is required to overcome these two type of the dissipation. One is the drag force, other is the force of friction. In the second part, you need to convert this power into kilowatt hour. What is the total energy in kilowatt hour? For the total energy in kilowatt hour, what you need to do? You need to multiply, because power also have a formula. P is equal to W over T, work done, or the rate of work. You can also write it as energy divided by T, and you want kilowatt hour, then multiply, isolate the energy is equal to P multiplied by T. So you don't have the time, but two things that you have to convert that into a time. You have the velocity, you have the cover distance. So let us make the formula. Energy in the kilowatt hour is equal to P multiplied by T, and T is actually the ratio of the cover distance divided by velocity, S over V, and P is actually 9.25 kilowatt hour multiplied by S is 500 kilometer divided by 120, and simplify it. Finally, you will have the value in the kilowatt hour. Power is equal to 38.54 kilowatt hour. 38.54 kilowatt hour. So finally you have converted. It was the result. Okay, let me show you here some values. Is it question number 5? Yes. Okay, mass of the vehicle is 1000 kg, and area of its tire facing the frictional force of the road is 0.7, drag force constant 0.28, and air density, that is 1.225, velocity 120 km per hour, that is converted into meter per second, and force of friction, coefficient of friction 0.015, and gravitational constant, that is 9.81. What you need to require? You need to find the required power. Which required power that is necessary to overcome the force of friction and drag force to maintain the constant speed of a vehicle. So I have converted this statement into an equation, that is F engine is equal to F drag plus F force of friction. Putting the values, simplifying, putting the corresponding values, simplifying, and finally we have the answer. Here you can see 277.5 Newton, and putting this value 9249 W, and simplifying, finally power is 9.25 kW. Total energy you have to measure in the kilowatt hour. So total energy required for the trip can be calculated by multiplying the power required to maintain constant speed by the duration of the trip. Simplifying, putting the values, and finally you have the result in kilowatt hour for the energy. So the total energy required for this 500 kilometer trip at a steady speed of 120 km per hour is 38.54 kilowatt hour energy. That is the energy required for that 500 kilometer trip. Is it clear?
Yes, it's clear.